Well, good afternoon, everyone. I'm Barbara Snyder, president of Case Western Reserve University, and on behalf of our university and on behalf of the Great Lakes Energy Institute, I'm delighted to welcome you to this National Academy of Engineering topical meeting, Perspectives on Global Climate Change. We are honored that Cleveland is the host to the National Academy of Engineering for the 5th time for meetings that bring science and technology to the public, which is incredibly important. As the nation's preeminent organization of more than 2,000 of the most exceptional engineers from across the country and the world, the National Academy of Engineering is well positioned to address a topic like today's by bringing together some of the greatest minds who are working to advance our understanding of global climate change. I want to thank the incomparable Arthur Hoyer, sitting in the middle there, Distinguished University Professor, Professor Emeritus in the Department of Materials Science and Engineering, and of course, an elected member of the National Academy of Engineering, and the other local Academy members here who helped make this meeting possible. It is also a great pleasure to be able to publicly thank Professor Alexis Abramson, who is sitting at the end and who is director of the Great Lakes Energy Institute, for hosting today's meeting. I want to recognize also the truly exceptional Phil Taylor, distinguished university professor and Perkins professor of physics, and I'm sure he's out there somewhere. He will conclude today's program. Oh, there he is. Phil, thank you so much for doing this. It is also wonderful to be able to acknowledge our sponsors, without whom we could not have this program. The Cleveland Foundation, the Key Bank Foundation, the Public Education on Technology and Science, the Kelvin and Eleanor Smith Foundation, IdeaStream, the Yun Yen Foundation, and Case Western Reserve Schools of Medicine, the Case School of Engineering, and our Office of Research and Technology Management. Today, we are fortunate to hear from some of the most knowledgeable scientists on one of the most pressing issues facing our entire planet, and that is global climate change. I am truly proud of the active role that Case Western Reserve has taken in studying and addressing the causes of climate change through the work of our Great Lakes Energy Institute and the many faculty affiliated with it. The Great Lakes Energy Institute, you should know, is celebrating its 10th year of advancing energy-related research, and we are really proud of that. Just a few examples. Roger French is working to improve the performance of solar panels, and Bob Sabanel, he has an all-iron flow battery that is an expensive, safe, clean way to advance the use of renewable energy on the power grid. We have an outstanding group of speakers who are going to leave us far better informed than we are already about the effects of climate change on our land, on the oceans, and on the atmosphere. And I also want to thank Professor Michael Mann from Penn State University, Professor Stephen Palumbi from Stanford University, and Dr. Ram Ramaswamy from NOAA's Geophysical Fluid Dynamics Laboratory and Princeton University for sharing their tremendous expertise with us today. I am now pleased to introduce Dr. Al Romick, Executive Director of the National Academy of Engineering. And before joining the Academy, you should know that he had an extraordinary career in industry, most recently as Vice President and General Manager of Lockheed Martin Aeronautics Company's Advanced Development Program, more commonly known as the Skunk Works. He's smiling as I say that. This is where some of the nation's most impressive aerospace innovation has taken place since 1943. Before moving to Lockheed Martin, Dr. Romick spent most of his career at Sandia National Laboratories, operated by Lockheed Martin, where he rose from a member of the technical staff shortly after finishing his PhD to become Deputy Director and Chief Operating Officer before transferring to the Skunk Works. Dr. Romick is a fellow of ASM International. He's a fellow of the IEEE and the IEEE, and the AAA, among many others. In 2003, he was elected to the National Academy of Engineering, and in 2008, the Council of Foreign Relations. We are so fortunate to have his leadership and wisdom and expertise here to help kick off our program. Dr. Romick, please take over. Thank you. Thank you so much.
Thank you. Well, after that, I'm not sure what I should actually do. That was very nice. Thank you so much. On behalf of the National Academy, our president, Dan Moat, and the rest of the leadership and all the membership across the country, I welcome you all to this event and thank you all for taking the time to come and participate. And of course, I thank Arthur and the rest of the planning and the steering committee that made this all possible, and a number of other names that are operating behind the scene, as well as the sponsors. Without any of those individuals or the sponsors, et cetera, this event certainly would not have happened. And as I think was said, Arthur, this is about the 6th time that you've done one of these things, and I'm already working on them for another one in about 2020, so we'll see where that goes. But I thought I would start by just telling you a little bit about the National Academies. I think a lot of people don't really realize what they are, or perhaps think that they're an honor society, and in fact they're not. It's an honor to be elected into the Academy, but it in itself is not an honor society like being the fellow of a professional society. The academies were actually founded as the National Academy of Sciences in 1863 under an act of Congress that was signed by Abraham Lincoln, and was done because in those deep, dark days of the Civil War, he believed that he needed technical, independent, objective information to be able to make decisions in the conduct of the war. The Civil War is arguably the first industrial war that the world had ever seen. We saw the introduction of iron and a number of other things. There were many issues in the Navy, in fact, around how you can make iron ships work, making corrosion issues, how you make magnetic compasses work, and so forth. He found that the shipbuilders, the iron makers, and the Navy all gave biased answers that were laced with self-interest. So we created this independent body called the National Academy in March of 1863. And for those of you that have served on National Academy committees, you know that we pay very, very well, because 0 is a nice round number. And all the work is done for free. Only expenses are actually covered when these studies are done. And issues around the climate and the environment have actually been with us since the very beginning. There were a couple of very prominent expeditions during the late part of the 1800s. Lake Powell, there was a Powell expedition that explored the West for timber and minerals and water, et cetera, led by Powell, Lake Powell, same guy, that's where it came from. There was later another mission led by Hayden, and that ultimately led to the creation of the United States Geological Survey. And in fact, to this day, when a new director is picked of the USGS, they will seek out the advice of the National Academies. As time went by, although it started founded by physicians and engineers and scientists, it became heavily science-dominated. And so over a period of time, there now are 3 academies, all organized under one great charter that's called the National Academies of Sciences, Engineering, and Medicine. And those of us here today principally are from the National Academy of Engineering, and we do have one member from the National Academy of Medicine who's actually a joint member between the two. And I would suggest to you that if you're curious about what the academies have done in the area of the environment and climate, if you go to the National Academy's press site, you can look up all the reports that have been done almost since the beginning and download a PDF for free of any of those individual reports that you would like to see. And in fact, as recently as 2016 at our annual meeting, the topic of the technical session there was on mitigation of sea level rise, which of course is one of the consequences. So it was a very, very popular meeting. It too is published and is available on the NAP website if you would like to look at it. So there's no doubt that this is a very important and topical issue for us. It's one that follows literally almost 150 years of history at the academies as being something that's important to us, and we're delighted to be able to sponsor the event that's occurring here today. I'll also point out that Arthur and his colleagues here at Case Western are again being trailblazing pioneers for us. We started a process a few years back where our sections that are organized by discipline could organize events like this. This one's a bit different. The members of the Academy that organize this are of different engineering disciplines. So this is a new category of meeting organized by members that we call a community meeting, because the members of the Academy, regardless of their discipline, gathered in the greater Case Western Reserve University community to put the event on. So thank you again for all your work. I hope the audience greatly enjoys this, and thank you, Arthur. And so I'll now turn the podium over to Professor Arthur Hoyer.
Well, with those introductory remarks, there's not much left for me to say. I had originally prepared a 70-minute talk, but it's been attenuated to be more like 70 seconds. Thanks for both to President Snyder and to Dr. Omick for those remarks. This is the steering committee. As you see, I've been the chairman, and Grant Goodrich, who is a co-chair, he's the director of the Great Lakes Energy Institute and has been a terrific partner for me. Trevor Jones is in the audience, member of the NAE, is finance chair. He does that with great aplomb. And then there's Jim Anderson, John Angus, Tom Barmich, who's our treasurer, Hunter Peckham. They're all those indicated are members of the NAE. Phil Taylor, who's already been mentioned by Barbara. And I want to particularly acknowledge Eric Wood, who was very instrumental in helping me put this program together in the early days back around New Year's. It's been a lot of work, as you can imagine, to put on a show like this, and we've been really blessed with terrific assistance from a number of people at Case Western Reserve University. I want to particularly acknowledge Lisa Chalk and Christine Kulik, the first two names there. Lisa is the secretary of this event and works in the Great Lakes Energy Institute, and Christine Kulik handles marketing for the Case School of Engineering. The fact that we have nearly a full house here is due to a tribute to her. She also has put together these programs. And the other members on that list are various people at Case Western Reserve who've worked very, very hard to put this together. I think my 70 seconds are up. I then can introduce Alexis Abramson, who's the co-director of the Great Lakes Energy Institute and Maltz Professor of Energy Innovations and interim chair of the Department of Electrical Engineering.
Well, thank you for everybody for joining us today. It's a pleasure to see so many faces out there in the audience. This is a very important discussion about climate change, and I'm looking forward to having your participation in that discussion as well. I do want to thank the National Academy of Engineering, particularly the steering and planning committees you just heard about, for co-sponsoring this event with the Great Lakes Energy Institute, where I'm co-director. GLEI supports the education, research, and commercialization activities of our faculty, our students, and our partners with a focus on energy and sustainability. This year, we are celebrating GLEI's 10-year anniversary. Thank you. So why does the world need an institute like GLEI here at Case Western Reserve University? Well, we're at a critical time in history, as we will hear today. Climate change is threatening so many aspects of our lives. In particular, increasing global temperatures, rising sea levels, and extreme weather events are forcing us to consider how we generate and use energy. So can we or should we continue to burn coal? What about natural gas? Is there a way to minimize the impact on the environment if we do? How fast can we increase the number of installations of wind turbines or solar panels? And how do we ensure that they stay high performance and cost effective so we all can afford them? Can batteries be used to encourage an even greater adoption of renewables? And can we or should we still rely on our aging transmission and distribution infrastructure for power? So to answer these questions, we need to engage, among others, technology leaders, engineers and scientists to ensure innovative and radically different approaches are considered. I am proud that GLEI and the teams with whom we work are catalyzing the technological solutions that are mitigating the environmental impacts we will hear about today. So before I introduce our first speaker, I have a couple of housekeeping items to go over with you. You all, when you came in, should have received index cards. Those index cards are to be used for your questions during the Q&A sessions. If you did not get an index card, you can raise your hand and people around the room would be happy to provide them to you. So we do have some hands raised and some people walking around to get you those index cards. So please write down your questions. During the talk, I want to see you writing away those questions that you have. And then please take those index cards as soon as you finish your questions. It can be in the middle of the talk, and pass them down the aisle. So that means you on the aisles there, you have a job. And your job on the aisles is to make sure that our students that are collecting the questions are able to get them from you. So you can recognize our students from Case Western Reserve University. They are the ones in the blue NAE hats. They're walking around now. So again, when those questions are ready, kind of hold your hand out, and they will be watching during the talks for you to hand them those questions. Those questions will then be passed to a small review committee and then passed to me so that I can facilitate the Q&A session. There will be 3 Q&A sessions, each one following each speaker, and then a general Q&A session at the end. If you have a preference for the specific question to be directed at one of our speakers or to be held maybe for the general session, just please indicate that on your index cards. So, with that, with great pleasure, I would like to introduce our first speaker. Michael E. Mann is a distinguished professor of atmospheric science at Penn State University and director of Penn State's Earth System Science Center. Using rigorous analysis and modeling of historical temperature patterns, Dr. Mann's work has contributed significantly to helping society understand climate change. In fact, his research contributed to the awarding of the Nobel Peace Prize in 2007, jointly to both Al Gore and the Intergovernmental Panel on Climate Change, on which he participated. He's received numerous honors and awards, including selection by Scientific American as one of the 50 leading visionaries in science and technology. Dr. Mann has authored over 200 publications, including 3 books, the most recent titled The Madhouse Effect: How Climate Change Denial is Threatening Our Planet, Destroying Our Politics, and Driving Us Crazy. And I plan to use this book in my seminar course on energy and sustainability in the fall. Dr. Mann received his bachelor's degree in applied math and physics from the University of California, Berkeley, and a doctorate degree in physics from Yale University. Please join me in welcoming Dr. Michael Mann to this stage.
Okay, well, thanks very much, Alexis. And I want to thank Al and Arthur and Phil Taylor, Case Western, the National Academies for sponsoring this event, which I'm very much looking forward to participating in. I am going to start out with a broad overview of the science, impacts, and solutions when it comes to the issue of human-caused climate change, based loosely on my book of the same title, Our Predictions, Understanding Climate Change. So we're going to try to understand climate change. We're going to try to understand the science. We're going to try to understand the impacts, which are no longer subtle. We are seeing the impacts play out in real time now. And we'll talk about the solutions, because there is indeed a way forward. The first point that I want to make when it comes to the fundamental science is that it's actually not that complicated, and it is not new or controversial science. The greenhouse effect, this is nearly 200-year-old science. Joseph Fourier, who lived so long ago we don't even have a photograph of him, just a hand-drawn portrait, he understood that the atmosphere had this warming impact on the surface of the planet. And over the past 200 years, we have been refining our understanding of the greenhouse effect and climate change. But the basics, the fundamentals, basic physics and chemistry that goes back nearly 200 years. The fact that we are increasing the greenhouse effect incontrovertible. We have been measuring the concentrations of these gases in the atmosphere in Mauna Loa and Hawaii since 1958, and we can extend the record back hundreds of thousands of years with ice cores. Now, this graph that I constructed a few years ago is now fundamentally out of date. You have to add another vertical tick mark to the scale because we've passed 400 parts per million CO2 in the atmosphere now for the first time in what we estimate to be millions of years. So we are engaged in this unprecedented, uncontrolled experiment with the one planet that we know of in the universe that supports life. What we wouldn't be able to explain, given the fundamental nature of the greenhouse effect and the irrefutable measurement of the increase in the greenhouse effect coming from the burning of fossil fuels and other human activities that produce these greenhouse gases like carbon dioxide, what we wouldn't be able to explain would be if the Earth were not warming up. That would stump the world's scientists. It has to be warming up. And it is. The measurements tell us it's warmed a little less than a degree Celsius. 2016 was the third consecutive record-breaking year. So 2014 was the warmest year on record until 2015, which was the warmest year on record, until 2016, which was the warmest year on record. The good news is that 2017 was not the warmest year on record, only the second warmest. So the critics will say, well, you know, it could be natural. I mean, these things happen. It could just be an unlucky streak. Well, we actually studied that. We used a combination of climate model, simulation results, and observational data to estimate what the likelihood would be of 3 consecutive record-breaking years, as we saw 2014, 2015, 2016, if it was just chance occurrence in the absence of human-caused warming of the planet. And I could read to you the abstract and talk about the p-values and the likelihoods, but instead I'm just going to put up the headline of the Discover article that summarized our findings. The record global warming streak of 2014 to 2016, a snowball's chance in hell that this was natural. That's a pretty good sort of lay description of our finding. So we know the planet is warmed up. We know it's not due to us. If it were natural factors alone, the planet should have actually cooled over the latter half of the 20th century. We can only explain the warming of the planet when we include the human impact of increasing greenhouse gas concentrations. So that's settled science. Scientists aren't debating that fact. And that's why the Intergovernmental Panel on Climate Change, in their most recent report, the IPCC, which is a conservative organization, after all, their reports represent sort of the lowest common denominator of what thousands of scientists around the world can agree upon. So by construction, these reports are conservative, some would even say reticent in terms of the way the conclusions are framed. And so when the IPCC says that it is extremely likely that human influence has been the dominant cause of the observed warming since the mid-20th century, even they are being overly conservative in saying so, because we are responsible for more than 100% of the warming that we've seen. And you've already seen the evidence for that. Natural factors should have led to a slight cooling in recent decades, and we warmed in spite of them. So we're responsible for all of the warming of the planet. Now, years ago, in fact, it was the 20-year anniversary as of Earth Day last month, of the hockey stick curve, a curve that we published back in 1998 and then extended in 1999, where we used indirect evidence from paleoclimate records like tree rings and corals and ice cores to extend the instrumental record, to extend the temperature record farther back in time, as far back as we could go, 1,000 years. And what we found was that the warming spike of the past century is unprecedented, as far back as we were able to go. There is something unusual about the warming that we are seeing today in a long-term context. It got a name, the hockey stick. It was featured in the summary for policymakers of the IPCC, and it's been attacked by the critics who have believed that if they can discredit this one iconic graph, the hockey stick curve, all of the evidence, all of the reason for concern over human-caused climate change would come crashing down like a house of cards, when in fact you could get rid of the hockey stick or the hockey league. There are many reconstructions that have now been done of this sort, and they all come to the conclusion that the recent warming is unprecedented as far back as we can go, more than 1,000 years. In fact, there's some indirect evidence that suggests that the warming we're seeing now is unprecedented in tens of thousands of years, and maybe longer. So we could get rid of this entire hockey league and it wouldn't make any difference. I outlined in the first minute or so of my talk the evidence for human-caused climate change, and it's basic physics and chemistry and irrefutable direct measurements of the changing concentration of these greenhouse gases in the atmosphere and the fact that the Earth is warming up as a result. But the hockey stick has remained an icon in the climate change debate, and even to this day, it is sometimes attacked. The IPCC has concluded that the recent warming is unprecedented, again, even further back in time than we had concluded 2 decades ago. In my book, The Hockey Stick and the Climate Wars, I sort of talk about what it's like as someone who's trained in physics and applied math, not a sort of career path that you expect to lead yourself into the most confrontational societal debate, the most fractious debate that we have ever had. But that is where I found myself as a result of this work. And I've come to embrace the role that that's given me to try to inform this larger conversation. So what about the future? What about the future projections? And Ram, my colleague, will be talking more about the climate models that we use, for example, to make future projections. What is likely to happen in the future if we act on this problem immediately, if we were able to essentially bring the burning of fossil fuels to a halt within the next decade and ramp down our emissions dramatically towards zero in the following decades, we could keep warming below 2 degrees Celsius, about 3.5 Fahrenheit relative to pre-industrial time. That's a level of warming. That 2 degrees Celsius warming is often pointed to as sort of the level of interference with the climate system that gives us dangerous and potentially irreversible impacts on our climate. We could avoid that if we act now. On the other hand, if we continue with business as usual, burning of fossil fuels, by the end of the century, we'll be somewhere between 4 and 5 degrees Celsius warming of the planet. That's 7 to 9 degrees Fahrenheit, twice that much in the Arctic because of the amplifying effect of melting ice. Well, let me show you an example of a climate model. And again, Ram will be talking more about these models. This is a sort of a business as usual scenario. We're moving into the future. We're going to go out to 2200, and by then we will have more than tripled pre-industrial CO2 concentrations. We're at 2000 in a few seconds. We are now into the future. We are into the future. And you might notice that there's still some cold winters in North America. Cold winters don't contradict the climate model simulations. There will continue to be year-to-year variability. You can see the El Nino events coming and going in the tropical Pacific. You can see the effect of changing jet stream patterns that give you warming and cooling in different regions. The climate system is very dynamic. And we will still get cold winters, but they'll get fewer and farther between. And the Earth on the whole continues to get warmer and warmer. You see what we call that Arctic amplification, even more warming in the Arctic, in part because of the melting of ice, the greater absorption of sunlight. At this point, you're starting to perhaps notice one other anomaly. That little cold patch south of Greenland in the North Atlantic, is that a glitch? It turns out it's not a glitch. That is the grain of truth to the movie The Day After Tomorrow. As we continue to melt ice and that fresh water runs into the North Atlantic and makes it fresher, that inhibits the sinking motion that drives what we call the conveyor belt, this warm current that warms the high latitude regions of the North Atlantic and parts of North America and Europe. And so we actually see that region in Greenland of cooling as that ocean current system slows down, and it decreases the warming a little bit in some of the areas neighboring the North Atlantic, but you don't get another ice age. You don't get tornadoes destroying the Hollywood sign in Los Angeles. there is a grain of truth to the movie, but it's little more than that. On the other hand, if that ocean current system were to collapse, that would have calamitous impacts, for example, on fish populations in the North Atlantic. And so there would be some dire consequences. This is an example of something that the model says we should see at the end of the century. You may have seen some news reports about a month ago. We are already seeing this. We are the better part of a century ahead of schedule now. Something that we thought wouldn't happen until the end of the century is actually happening already. We see evidence of that cold patch in the North Atlantic that signifies the slowing of this ocean current system. Well, let's talk a little bit more about some of the other changes, like the decrease in sea ice. The critics will sometimes try to tell you that the climate models are alarmist. They're overestimating the problem. Well, what I'm showing you here, the shaded region, is what the last generation of climate models predicted for the decrease in the sea ice in the Arctic in the late summer. And so the gray shaded region shows you the range of what the models predict. The red curve is the observations. And you'll see the observations are below the spread of the models. We're losing Arctic sea ice faster than the models said we should. The models say we may completely lose the sea ice perhaps by 2100. The observations, if you extrapolate them, say that we could see that in a couple decades. So once again, uncertainty is not our friend. If anything, the models have been overly conservative, and because they may be missing some of the processes that in the real world can actually act to accelerate things like the loss of sea ice. This is where we are this year as we head into the summer. The blue curve is where we are. The gray shading is the range of what we've seen in the past. And so, yes, we're outside what we've seen in the past. If we continue on this trajectory, we will set a new record for minimal Arctic sea ice at the end of the summer. Extreme weather events. We know that as you warm up the planet, heat waves become more pronounced, they become more extended. That's pretty obvious. The atmosphere gets warmer, so it holds more moisture, and so you can get more flooding, and we're seeing that. You can actually get worse drought as well, because warmer Earth evaporates more moisture into the atmosphere. So we expect more weather extremes for these reasons, but we published last year an article showing that there's another mechanism. In addition to everything I just talked about, there's another mechanism by which the amplified warming of the Arctic may in fact be changing the behavior of the jet stream, changing the behavior of the jet stream, in particular in the summer, in a way that gives you much larger wiggles, much larger meanders. And the larger the meanders in the jet stream, the bigger the weather anomalies. When you see big wiggles in the jet stream, some place is a lot warmer than it normally is, some places a lot colder, some places a lot wetter, some places a lot drier. And when those meanders get stuck in place, then those same regions get baked day after day or rained upon day after day. And what we've shown is this pattern of amplified Arctic warming through a subtle mechanism that actually relates to some of the physics of waveguides and quantum mechanics actually causes the jet stream to behave in a way where you get these large meanders and they stay locked in place, potentially for weeks at a time. And that's what happened during the 2003 European heat wave, the 2010 Siberian wildfires and the Pakistan floods, the 2011 Texas and Oklahoma drought and heat wave, the 2016 Alberta wildfires. All of those phenomena were associated with this jet stream phenomenon. Tipping points. So not everything in the climate system behaves smoothly, which is to say you can be pushing on it, you can be forcing it, and all of a sudden the system rapidly transitions from the state it was in to a completely different state. We call that a tipping point. And we know of tipping points in the climate system. The collapse of the thermohaline circulation, the conveyor belt ocean circulation that I talked about, that's an example of a tipping point. If we freshen the North Atlantic enough, then that ocean circulation system just shuts down suddenly, and you get very abrupt climate change impacts. The loss of ice from the ice sheets, the Greenland ice sheet, the West Antarctic ice sheet. Again, a tipping point. Once you warm the system enough, and we're seeing this now in Antarctica, we've destabilized the ice shelves, and these ice shelves are sort of like buttresses that help prop up the Antarctic ice sheet. And when you lose those ice shelves, suddenly the inland ice can start to surge out towards the ocean. And we're discovering that there are some feedback mechanisms that act to accelerate that process once it begins. Everything that we're learning is increasingly pushing us towards higher estimates. This was from the last IPCC report, and you see a predicted sea level rise, a maximum of about a meter, about 3 feet by 2100. Within the last year and a half, we have doubled that estimate. We're now saying 6 to 8 feet of sea level rise potentially by 2100. And that's just in the space of a few years as we've started to put some of the processes into the models that were missing. We found that that ice sheet collapse process can take place much more quickly. And so we've literally doubled the estimate of the sea level rise we could see by the end of the century. Uncertainty is not our friend. There is uncertainty, there is scientific uncertainty. It has not been our friend. As we understand more, if anything, the projections are moving towards faster and larger changes than we had predicted in the past. And we're starting to understand that there are mechanisms that we're missing from the models, again, that can accelerate these processes. Now, that's in the real world. That's according to the National Academy of Sciences, founded by Republican President Abraham Lincoln, as we heard earlier, or all of the scientific societies in the US and in Europe, all of which have weighed in. The world scientific community has weighed in. Climate change is real, it's human caused, it's already a problem. Sea level rise in particular represents an existential threat to our coastlines. But some of our lawmakers, you may have read this in the news, there was a hearing of the House Science Committee a week ago where one leading congressman insisted that the cause of sea level rise is rocks tumbling into the ocean. And so that is our House Science Committee. So on the one hand, you have the overwhelming consensus of the world's scientists. On the other hand, you have the people who are actually making policy right now, at least in the United States. And at almost the same, I think just within a day of that, was an op-ed in the the Wall Street Journal, which frequently opines in a contrarian manner when it comes to the science of climate change. An op-ed that insisted the sea is rising, but not because of climate change. Well, yesterday we actually published a letter to the editor in the Wall Street Journal that I'll put up here, where we pointed out that they might as well have published an op-ed about how objects are falling, but not because of gravity, because it's about as absurd. There were actually several letters to the editor that were published. And I know that at least one person read this letter to the editor that we wrote because I was sitting next to him on the plane to Cleveland yesterday. One of the things we pointed out in our letter is, by the way, Hurricane Sandy caused 25 square miles of additional flooding due to 1 foot of sea level rise. 1 foot of sea level rise meant 25 more square miles of flooding in New York City and several $1 billion of additional damage. 1 foot. Now imagine what 6 to 8 feet would do. As we pointed out in our letter, 6 to 8 feet of sea level rise would submerge Wall Street. The Wall Street Journal actually isn't located in Wall Street, but... And Hurricane Sandy-like storms, we published an article a year ago showing that when you take the effect of global sea level rise on top of the effect of intensifying hurricanes, it turns out that a Sandy-like storm surge of, 12 feet, New York City, which today we estimate to be roughly a 30-year event. It's something we don't expect to see any more often than 30 years, once in 30 years. Before we started warming the planet, it was more like a 300-year event. But we've increased that to about a 30-year event. If we continue with business as usual, burning of fossil fuels, and warm the planet by 4 to 5 degrees Celsius by the end of the century, then a Hurricane Sandy-like event becomes a 3 to 4 year event. Imagine New York City dealing with a superstorm Sandy every 3 to 4 years. At that point, we're talking about the retreat from our coastlines. And some people say it's going to be expensive to do something about climate change. It's going to be a lot more expensive not to do something about climate change. So the impacts, I've already alluded to them. Business as usual, burning of fossil fuels. It's not just about polar bears. I care about the polar bears. But sometimes when we make the polar bear the poster child of climate change, it makes climate change seem like an exotic, far-off problem when it's not. It's a problem here and now. It's impacting us in real time today. We see it play out on our television screens and our newspaper headlines. Now, it's also about the threat to our coral reefs from coral bleaching combined with ocean acidification. And Steve will be talking more about that and other threats to our oceans in his talk. In fact, a year ago, there was an obituary written for the Great Barrier Reef. It was only slightly tongue-in-cheek. Something like 90% of the Great Barrier Reef was bleached in the last El Nino event. And based on the trajectory that we are on, there are an increasing number of scientists who think that we could see the end. We could literally see the death of the Great Barrier Reef within a decade or two if we continue on the course that we're on. Unprecedented droughts, like the one that California has dealt with, the worst drought on record, and their governor, Jerry Brown, has been very proactive on the issue of climate change. He's raised awareness about the very real threat that California is feeling today. And let me add that he knows where to get his science. So a record drought in California has had a profound impact on us. But let's talk about another record drought in Syria. California just had the worst drought in at least 1,200 years. That's what the paleoclimate scientists tell us. They can only go back 1,200 years with the records they have. It may be the worst drought over a much longer time frame, but they can only go back 1,200 years. In Syria, they can only go back 900 years. And the drought that Syria has faced over the past decade is the worst drought on record as far back as they can go, 900 years. What did that drought do? It forced rural farmers into the cities where they were now competing for food and water and space with the people who already live there. That creates competition and conflict. And it was in that atmosphere of conflict that the organization ISIS arose. So when our president says we shouldn't be talking about non-issues like climate change, we need to focus on the real problems like international terrorism, that is a false dichotomy because, in fact, as our national security community has made very clear, climate change is a threat multiplier. It is the greatest national security threat that we face because it takes existing tensions and existing competition and it exacerbates it. And they have connected the dots now between this unprecedented drought and the emergence of groups like ISIS. This is a national security threat. It's the biggest national security threat we face. And wildfires, unprecedented wildfires like the one in California last winter, and that you might think, what do you mean last winter? California doesn't get wildfires in the winter, they get it in the summer. The summer fire season is the summer. The worst wildfire in California history now was the Thompson Fire that occurred last winter, an out-of-season fire. And as the earth dries out, as temperatures warm up, we're going to see an expansion of the fire season, of the dry season, the fire season. By the way, that fire nearly destroyed Rupert Murdoch's estate. So it's sometimes said that sometimes people won't act on a problem until it hits home. Well, with Rupert Murdoch, it's hit home now. So hopefully we may see more enlightened coverage of the issue of climate change in the Wall Street Journal and Fox News and the other Murdoch outlets, now that it's truly hit home for Rupert Murdoch. Now, you had this massive wildfire, these wildfires in Southern California, which weakened the soil and killed off the vegetation. And then in the winter, of course, you'd finally get that rainfall. And by the way, when it rains, you get more of it. Floods get worse because of a warmer atmosphere holding more moisture. So when those winter rains came, as we expect them to do, they occur in shorter, more intense bursts. So you've got topsoil that has lost its integrity because of the wildfire. You've got extreme flooding. Those two things come together, and you get sort of mudslides that we saw in Southern California. And this really points to the unintended, or not the unintended, but sort of the unanticipated potential consequences. Only when we look at this in retrospect can we say, it's the warm conditions and drought that created the conditions necessary for these wildfires, which then created the conditions necessary for winter mudslides. It's all connected. And hurricanes, unprecedented. Harvey, the wettest event in history, the most intense flooding event in U.S. history. There's already, even months later, there's now literature, in the peer-reviewed literature, showing that we would not have seen that amount of flooding in the absence of human-caused climate change. Human-caused climate change didn't create Harvey. It didn't cause Harvey. It made Harvey worse. It took what would have been an intense flooding event and turned it into a record flooding event. And then we had Irma, the strongest storm ever in the open Atlantic, and maybe that's a coincidence. Over the last few years, let's see, we've had the strongest storm ever in the open Atlantic, the strongest storm ever globally, that was Patricia in the North Pacific, the strongest storm ever, obviously, in the Pacific, and in the Northern Hemisphere, that was Patricia, the strongest storm ever in the Southern Hemisphere, that was Winston, during a period at which the oceans have been at the warmest they've ever been on record, and where we know the physics that is involved. As you warm the ocean surface, there's more energy to intensify these storms, and there's more moisture in the air. Warmer ocean surface means more evaporation, more moisture into the air, moisture that is turned into rainfall on land. So there is a direct connection between this unprecedented storm season that we had, and we're just about to start the next one now. And Puerto Rico still hasn't quite recovered from the devastation of Maria, another near record intensity storm that decimated Puerto Rico. There are still people without drinking water and power a whole hurricane season later. And so, as I said before, the impacts of climate change are no longer subtle. We are seeing them play out in real time in the form of unprecedented superstorms and floods and droughts and heat waves and wildfires. By some measure, dangerous climate change has arrived. If you're Miami Beach, now perennially flooded just by a high enough tide, it doesn't even take a storm anymore, and you're building millions of dollars infrastructure to desperately try to pump the water back out to the sea in a losing effort to fight the encroaching seas, dangerous climate change has arrived. If you're in Syria, dangerous climate change has arrived. If you're suffering the consequences of the national security implications of the Syrian drought, which we all are, dangerous climate change has arrived. If you're a low-lying island nation that's regularly flooded now because of rising seas, dangerous climate change has arrived. If you're a farmer in Texas or Oklahoma who lost 25% of their cattle in the 2011 Oklahoma-Texas drought, a drought, by the way, that the peer-reviewed literature now says would not have happened. We would not have seen that record drought in the absence of climate change. It exacerbated. A bad drought turned it into a record drought. Or California, a California farmer, or somebody who lost their home, or somebody who lost their lives in any of these events, including the catastrophic Hurricane Maria as it struck Puerto Rico and impacted American citizens in Puerto Rico. So what do? The problem is now clear. It's time to get past this unworthy debate in our politics about whether climate change is real and onto the worthy debate to be had about what to do about it. And yes, we will need to do some adaptation. There's a certain amount of additional warming, a certain amount of additional sea level rise and aridification that's already baked in. That's going to occur no matter what we do, just because of the inertia of the climate system. So there's already a certain amount of additional climate change that's baked in, and we're going to need to build the infrastructure to adapt to the changes that are in store, to increase our resilience in the face of increasingly devastating extreme weather events. We will have to do some amount of adaptation. But if we don't act to mitigate the problem, to stem the problem at its source, the increasing warming of the planet, we will exceed our adaptive capacity. We will exceed the adaptive capacity of other living things. We cannot adapt to the climate change that will happen if we don't act on this problem now. So what are the solutions? Some would say, for example, our former Secretary of State, Rex Tillerson, a former CEO of ExxonMobil, and maybe that has something to do with his views about how to tackle climate change. No, let's continue to burn those fossil fuels, but you know what we'll do? We will geoengineer the planet. We'll do something else. We'll engage, and since this is an event that, under the auspices of the National Academy of Engineering, the idea is that we take this system that we don't understand perfectly. We engage in a planetary experiment where we manipulate this system by throwing particles up into the stratosphere or dumping iron into the ocean to try to change the ocean carbon cycle, fertilize algae, put reflecting mirrors in space. What could possibly go wrong? Which is in fact the title of our chapter in the Madhouse Effect, Geoengineering, or What Could Possibly Go Wrong. Of course, we're dealing with the principle of unintended consequences, and we could very easily end up with an even bigger problem than the one we started out with. So with some narrow exceptions, geoengineering is probably not the path forward. There is no magic bullet. It's about personal actions. There's a lot that we can do individually to lower our carbon footprints, to go from a Sasquatch to a Cinderella carbon footprint. And a lot of those things save us money. They make us healthier. Low-hanging fruit, we ought to do them anyways. But individual actions alone aren't going to get us to where we need to be. If we are going to make the reductions in carbon emissions, if we're going to ramp down those carbon emissions fast enough to avoid catastrophic climate change, we are going to need market incentives. We are going to need to solve this problem at the highest level. We need to fundamentally transition away from a fossil fuel global energy economy to a renewable energy economy. And there's a worthy debate to be had, and there are conservatives and progressives of goodwill who are participating in that discussion. That's the debate that we ought to be having in our U.S. House of Representatives, not is sea level rise caused by rocks falling into the ocean. We have to stop this unworthy political debate and own up to the fact that the problem is real, the threat is real, and there's a legitimate political debate to be had about how we solve it. And I have good friends who are conservative Republicans like Bob Inglis, a former congressman from South Carolina, who was primaried out of his seat and replaced by a man named Trey Gowdy. He is a conservative who travels around the country talking about market solutions to solving this problem that are consistent with his conservative ideological principles. Let's have that discussion, and I'll leave it there. Thank you very much.
We will be continuing with a short question and answer period for Dr. Mann here. If you haven't yet, please give your questions to some of the students going around with the hats, and they will start collecting. How do you know your models are right?
How do we know our models are right? It's a great question, because we spend all of our time, good scientists are skeptics. is a term that has been abused in the public discourse. There's been an attempt to claim the mantle of skepticism. Those who are not skeptics, they're basically contrarians. They reject the overwhelming, scientific evidence in favor of crackpot theories. That's not skepticism. Real skepticism is what's practiced by scientists. You're always looking for how you might be wrong. You're always double-checking your calculations. And here's the good news. Even if you screw up, you've got thousands of other colleagues around the world who are doing the same thing. And if you're wrong, you're going to be found out to be wrong. That's what Carl Sagan described as the self-correcting machinery of science. Science has this wonderful self-correcting machinery. It's peer review. It's the scientific give and take that takes place at conferences. And so, in a sense, we are always wrong because we've never solved. There's no problem of a global scale that has been completely solved. In physics, there are still wide open problems. We still haven't observed a graviton, so I sometimes say to my colleagues, well, the theory of gravity, isn't yet, there are fundamental uncertainties in the theory of gravity because we haven't observed a graviton. That doesn't make it safe to jump off a cliff. And yet there are those who would have us jump off the metaphorical cliff of not acting on climate change given similar levels of uncertainty.
And one of our audience members had a sort of a complementary question to that is, every year we're gathering new data. So how much does the accuracy of the models change as we gather that data?
Yeah, it's a great question. There's sort of a give and take where, we do our best. The models, and it's important to understand, the models are simply a way to formalize our physical understanding of the system. The climate system is too complicated to do a Gedanken experiment, like Einstein, proposed. You actually, when you're dealing with complex systems, you actually have to solve the physics. You have to put the physics in and try to understand all of the interactions between the physical components of the system and the chemistry and the biology. It's an amazingly complicated problem. And so there is this constant refinement where we try to improve the processes in the models, and hopefully, if we do it right, we get better agreement with the observations. And when we fail to get better agreement with the observations, it tells us that there's probably still something missing. And one great example is what we've seen with ice sheets, where for a long time, the process people, the people who are out there in Antarctica and Greenland, measuring stuff on the ground, digging holes, figuring out what's going on, we're saying, your models are way too simplistic. Basically, the climate modelers were treating ice sheets as big mounds of ice that are very sluggish, and they melt slowly, like that last mound of ice in the late winter that still sits there in the corner of your lawn, in the dark area of your lawn. That's not how ice sheets behave. They're very dynamic. You have these ice shelves that prop up the ice sheet, and when those ice shelves get melted from a warming ocean from beneath, you destabilize the ice. And then it turns out a colleague of mine, Dave Pollard at Penn State, along with Rob DeConto of the University of Massachusetts, published this blockbuster study in Nature a year and a half ago where they showed that with Antarctica, what happens is you erode an ice cliff. The ice shelf is propping up the inland ice. You have this cliff of ice right at the edge of the ice sheet, and it collapses. And then because of the sloping bedrock of Antarctica, the ice cliff behind it is taller. And when that one erodes, the ice cliff behind it is taller. A taller ice cliff is more likely to collapse on its own weight. And that's actually what's happening. And it's taken us from 1 meter of sea level rise by the end of the century 5 years ago to 2 meters of sea level rise now.
And I think we've all seen, or many of us, I'm sure, have seen those videos of those collapsing ice shelves. So very impactful in terms of when you're watching that. With all these complexities, impacts around the globe. I mean, we're using these terms like global warming or climate change. Are these, this is a question from our audience, are these the right terms? Should we be using other terms? What's your opinion on that?
There's a funny story here because back in the early 2000s, in 2002, there was a memo that was leaked by a Republican pollster, Frank Luntz, and he was advising his clients, basically fossil fuel interests, in how they should be gaming the language. to try to allay concern by the public about the problem of climate change. And he actually advised them to use climate change rather than global warming because it sounds less threatening based on his focus groups and his polling. The irony is that scientists prefer to use the term climate change because it's a more general description of what we're talking about. The warming of the surface is one consequence of the buildup of greenhouse gases, but we've talked about so many others: the melting of ice, the shifting of rainfall patterns, changes in the jet stream. There's this much more diverse set of consequences that is what we call climate change. So ironically, the scientists are sort of in agreement with the Republican pollster Frank Luntz, who, and you often hear people say, well, the scientists changed the wording because they wanted to sound more alarmist. No. We actually use climate change now in favor of global warming. According to Frank Luntz's polling, that actually raises less alarm in the public mind.
Sure, I could see that. Now, at the end, you talked about some solutions, so I think everyone appreciated that. Maybe you can expand a little bit on some of the science that you may or may not know about, and to the extent that you do, with regard to carbon sequestration, because there seems to be a lot going on in the news right now about putting carbon back into the ground.
Yeah, well, and part of it is driven by the fact that as we continue to not meet sort of our targets. Last year, we were hoping that our CO2 emissions had hit a plateau. They had done so for a few years. A plateau is the first step. We've got to bring them down to zero. As long as those emissions are positive, CO2 continues to accumulate in the atmosphere. So bringing it to a plateau was a good start. And we thought we had reached it, and then last year it actually inched up again. And so with each year where we don't achieve the progress that we'd like to, and we come closer and closer to burning through that budget, the carbon that we can afford to burn through and still remain below that catastrophic 2 degrees Celsius warming, there's more and more discussion about the need for negative emissions. It's like we're not going to get there without now actively taking CO2 back out of the atmosphere. When you do that, you're fighting the laws of thermodynamics and the laws of economics. But it can be done. It's extremely expensive to, for example, to directly capture CO2 from the atmosphere. It's easier if you do it at the point of the burning of the carbon. So at a coal-fired power plant, you capture the CO2 and you bury it. But it turns out that coal is no longer competitive against other forms of energy, even without sequestration. So you add the requirement that they have to capture and sequester their CO2, it no longer makes any sense economically. Why don't we just invest more in the technology that we know can solve this problem, renewable energy?
Stop putting carbon into the atmosphere altogether, so good. So we're going to shift a little bit to the political climate. You had alluded to a bit in your talk. What steps do you recommend for climate change professionals like us to avoid the political persecutions that we sometimes see that you referenced in your talk?
Hide under the table. No, I'll tell, I sort of found myself in this world that I never expected to be in when this hockey stick, this iconic graph was published in 1998 and then extended in 1999, and suddenly I was in this completely different world. The world of science has certain rules of, fact-based discourse and logic and making an objective case and for your conclusions, but the world of politics doesn't invoke any of those rules. It doesn't work. And woe be the scientist who doesn't quickly recognize that they're in a completely different game when they're now dealing with the larger and very fractious public debate over climate change. So if you're a scientist and you want to be a prominent voice and you want to inform this discussion, recognize that you're going to be attacked because you're threatening their client. You're a threat to their client. They're going to come after you. Develop a thick skin. Understand that it's not about you. Understand that the attacks are not as personal as they might seem. They're not about you. Sure. They're about the fact that you're hurting their client, the case that you're making, and you're doing a good job doing it. And understand that there's a lot of support now in the scientific community. There's a lot of infrastructure now to support scientists who find themselves under attack. Back when I was first attacked, that didn't exist. One of the things that I've helped do is create what's known as the Climate Science Legal Defense Fund. A young scientist who receives a Freedom of Information Act request demanding all of their personal emails by some group that's looking to discredit them and take them out of context. Usually your university will cave. Your university, their first instinct is to cave. Their interests aren't necessarily aligned with your interests, so you need independent representation. And so we created the CSLDF, Climate Science Legal Defense Fund, for young scientists who do find themselves in that situation.
Great point. Okay, we will stop there. I know we didn't get to everybody's questions, but we'll hold on to them for the general question and answer session. Let's please thank Dr. Mann again for his wonderful talk.